In the previous class, we have discussed what all the shock waves are, the different types of the shock waves, and something the basics we have gone through. Next, what exactly the shock waves? They are the waves which are produced in a very small region of around a few microns, where the volume decreases and temperature, density, the pressure, it increases. And different types of the shock waves also we have gone through. Now to continue with this one, to study those shock waves, so we are using some parameter called as control volume. What exactly this control volume is? So control volume, it is a model on the basis of which the shock waves are analyzed. It's a model which based on that one the shock waves can be understood properly. Moreover, it is an imaginary thin envelope that surrounds the shock front, within which there is a sharp increase in pressure, temperature and density in the compressed volume. So what is the meaning of this one? So it is an imaginary layer. You can observe here, this is the shock front where the shock waves are produced. So the thin region is surrounded by a envelope, an imaginary surface. The dotted line is the imaginary surface that is known as the control volume. So in the control volume, when we can consider what that control volume is, it is an one-dimensional confinement in the medium. So it is a one-dimensional, which is moving in one-dimensional confinement in the medium with two faces. What are the two faces? It has pre-shock side. So this region is known as pre-shock side, where Mach number is greater than 1, and the region next to the shock front, so that region is known as post-shock side, where the Mach number is less than 1. So this control volume is having two faces, we can say. Here the left side is called as pre-shock, Mach number greater than 1, and on the right side it is a post-shock, where Mach number is less than 1. It's an imaginary surface within which the shock wave is present. This is the dark line what we have made, that is the small region where the shock wave is present. And for this one, what we have taken, ρ1, u1, t1, h1 and p1, what they corresponds to the parameters in pre-shock side, and ρ2, u2, t2, h2 and p2, they corresponds to the post-shock side values. What the values are? The ρ corresponds to the density, u the flow velocity, and T is the internal energy, H is the specific enthalpy, and P is the pressure. One corresponds to before and this is after that one. Second, 2 corresponds to. That is, and the entire shock is bound between two surfaces. Those two the surfaces. In control volume, the heat energy is constant. This is important. The heat energy is constant. So the whole process is going to be adiabatic process. So it is going. So this process is considered as the adiabatic process. So let me repeat once again. The control volume, it is here the dotted line. It is a thin imaginary layer which is surrounding the shock waves. So left side, before it is known as the pre-shock region, where Mach number is greater than 1, and on the right side it is the post-shock side, where Mach number is less than 1. For this control volume, whatever the control volume we have considered, so it is going to obey the law of conservation, okay, in connection with the law of conservation of mass, the law of conservation of momentum, and law of conservation of energy. And for this one we are taking that the control volume as a closed system. What is the meaning of closed system? A closed system, it is the one that does not exchange any matter with the outside and is not acted on by outside force. So this is the meaning of that system is closed, means it is not influenced by the external the matter. Okay. Now with this, we are going to apply the law of conservation with matter, momentum, and energy. So this law of conservation of mass we have studied in our PU. What it states: the total mass of any isolated system remains unchanged and is independent of any physical, chemical changes that could occur within the system. So this is the statement, means the mass is conserved, irrespective of that it is independent of the physical and the chemical the changes what it takes place. So it is given by mathematically rho 1 u1 is equal to rho 2 u2. The mass is conserved. This is in connection with the conservation of the mass. Second one is law of conservation of momentum. That is, in a closed system, the total momentum remains constant. Simple. In simple words, it is mentioned. Total mass is conserved, and here we can mention it is total momentum is conserved. Total momentum remains constant. And how it can be stated? This already in PUC we have gone through. That is, when two objects collide in an isolated system, the total momentum of the object before collision is equal to the total momentum of the object after the collision. It means before the impact the momentum and after the impact the momentum, both they are same. So this corresponds to the conservation of momentum. Mathematically it may be given as P1 plus rho 1 u1 square is equal to P2 plus rho 2 u2 square. So this is law of conservation of momentum. Then last is law of conservation of energy. What it states? The total energy of a closed system remains constant and it is independent of any changes occurring within the system. Here the total energy of the system remains constant. That is known as law of conservation of energy. It can be stated as mathematically h1 plus u1 square by 2 is equal to h2 plus u2 square by 2. So with these laws of conservation, now we will move to the ready shock tube. So he is a Professor C.K. Reddy. He is from IISc, Indian Institute of Science, Bangalore. Okay. So he has developed a shock tube. It's a hand-held the shock tube. It means within laboratory the shock waves can be produced. So what is the description of this one? So description is such a way that it is made up of a stainless steel tube, okay, which has got two sections. Both they are of 50 centimeter. This is different of 50 centimeter, and this is another. So two tubes. So these are the two tubes. So they are joined. There is a provision to join them. So both they are of 50 centimeter length. Altogether it is 1 meter. And the diameter of this one is 30 millimeter. So 30 millimeter is the diameter of this a cylindrical stainless tube, which is of each they are of length 50 centimeter. Next, here the provision is such a way that here in the left side you can observe there is a piston. It's a hand-held piston. Okay, so this and at the center, the red color what I have shown, there is a provision to add a diaphragm. So this diaphragm, it may be of thickness 0.1 millimeter, and it is made up of aluminum, or even usually it is made up of paper. Very thin paper we are that thin paper, the diaphragm, it separates these two stainless steel compartments. So this region we are going to call it as driver section, and whatever the gas we insert here, it is called as driver gas. And the other compartment is known as driven section, where the test gas, it means the test gas means the gas in which we are interested to study its the gas dynamics. Okay, so that particular gas is inserted here, that we call it as test gas. And the other end of this, the driven section, is closed, it is sealed. Now this, the end we call it as downstream end, and here on the left side we call it as upstream end. So this is a simple two stainless steel of 50 centimeter each of 30 mm diameter. On the left side the piston is there, and the right side it is closed, and at the center the diaphragm is used to separate these two regions. And in the driver section, so we use digital pressure gauge, means to maintain some high pressure we use the pressure gauge. And here on the driven section, two pressure sensors are there, S1 and S2. So this S1 and S2, in turn these pressure sensor, they are in turn connected to the CRO, that is cathode ray oscilloscope. This we'll discuss later. Now, what is the working of this one? The working is such a way that whenever we take the gas at high pressure, here the test gas is there, the piston is moved very rapidly, very fastly. This piston is moved, so that what happens, the gas which is at high pressure, it is pushed in the forward direction. Once this is pushed in the forward direction, the diaphragm, which is of very thin 0.1 mm thickness, it ruptures. So due to this, the gas, it rushes into the driven section. This gas, it moves into the driven section, and further this test gas is moved. So here, once the diaphragm ruptures, at that time the shock waves are produced in the driven section. So these shock waves which are produced, they move in the forward direction. They move in the forward direction, and it's those pressure are realized by S1 and S2. Then the shock wave which has moved, okay, here what happens, the pressure increases in this driven section, pressure increases, volume decreases, temperature is going to increase, very high temperature we are going to attain. Okay, now the shock wave which is produced, it moves towards the downstream end. Next what happens, it reflects back, and in the reflected section, once again S1 and S2, the pressure is measured. Now what happens, once the piston, when we move it in forward direction, at that time the diaphragm ruptures, at that time there is a back impact. So due to that, what happens, the piston is moved in the backward direction. At that time, the gas which it pushes that piston in the backward direction, okay, that gas, it comes and hits the piston and once again moves in the forward direction. That gas, it comes and it nullifies this shock wave which is reflected. Thus, the shock wave which is produced, it can be nullified, its effect can be nullified. Okay, so let me repeat once again. Here the gas is taken at high pressure, compared to this one in the test gas. Now once the piston is pushed at that time with a great pressure, the diaphragm ruptures and driver gas enters into the driven section. Due to this, the shock waves are produced. Shock wave moves in a forward direction and hits this downstream end and reflects back. But during that time, due to this impact, some gas, okay, it opposes this piston movement and it bounces back. And that gas, it hits the piston and once again moves in forward direction. It comes and it nullifies the effect of this particular, the shock waves which are produced. This is the construction working of the ready shock tube. Moreover, it is a handheld, okay, the handheld operated apparatus where within the laboratory we can produce the shock waves. And here S1 and S2 shock waves are produced and they are reflected. So those S1 and S2 once again are noted. So these are connected to the CRO, that is known as cathode ray oscilloscope. So very high CRO, okay, of 1 megahertz we have to choose, such that then based on the timing and the pressure, okay, we are going to calculate the further all parameters. Then what are the, that's what is the data collected from S1 and S2 through CRO, the Mach number, the pressure and temperature can be calculated. Then what are the characteristics of this particular the ready shock tube? It operates on the principle of free piston driven shock. We are using the piston. Second, it is a hand operated, as we have discussed here, and it is capable of producing Mach number exceeding 1.5. More than 1.5 Mach number we can produce with this a small setup. The rupture pressure is a function of the thickness of the diaphragm. Based on the thickness of the diaphragm, the rupture pressure varies. Usually a thin diaphragm we are using. So even as I said, temperature is increasing. A temperature of more than 900 Kelvin can be easily produced with this handheld operated ready shock tube. Then we'll come to the last part, that is what are the applications of these shock waves. The shock waves, they are used to, first one is cell information. See, by passing the shock waves of appropriate strength, so DNA can be pushed inside the cell without affecting the functionality of DNA. It's a biological application. The DNA can be it can be pushed into a healthy cell without affecting its the functionality. The next is wood preservation. What is the wood preservation? See, some bamboo you take, it is a hollow inside. So to keep it away from the bacterial effect, so we take the shock waves and the preservative in the form of the solution we take, and we pass the shock waves such that the preservatives it get in throughout the uniformly, it is distributed throughout that particular bamboo, and it's what happens, the maintenance, okay, it can be reduced. So we can increase the lifespan of that particular bamboo. Likewise, it can be used in a wood preservative. Next, use in pencil industry. So what happens whenever we are using in a pencil industry, we take the wood, we soak it in a polymer for 70 degrees for a few hours, then we have to dry it, then it is ready for to use. It will take more than 1 or 2 days. But if you make use of this particular shock waves, and the wood is particularly placed in that particular liquid, and when shock waves are passed through this liquid, so easily that liquid it soaks, it gets inside instantaneously into that particular the wood, and it is easy to dry. Even it requires very less time to dry, and within few hours now it is ready for the manufacturing process. So in large quantity, so this method can be adopted. The next one is kidney stone treatment. The shock waves, once again, of appropriate strength whenever they are used to break the kidney stones and the gallstones without surgery. So without surgery, we use the shock waves externally to break the kidney stones into small fragments, and it is passed through the urine. So this is the another application. The next one is the gas dynamics. It means gas dynamics, the previously as I discussed here. So in the driven section, we take the gas, the interested gas, and we produce the shock waves, and here we produce very high pressure, high temperature, and volume decreases, density increases. So all these, the gas, we call it as the gas dynamics. Its properties can be studied in laboratory. It is a very simple method, okay, to study the gas at extreme temperature and pressure. It can be easily studied with the shock waves. The next one is the needless drug delivery. So whenever the drug has to be delivered through the injection, so some pain will be there. To avoid that one, what happens? It's a painless process where the drug is filled in a cartridge. There is no needle, and this cartridge is held against the skin, and when shock waves of small strength is passed, then with that, under the high pressure, the drug directly gets into the skin. So without any pain, the drug penetrates through the skin, and it acts as a needless drug delivery. And one more is the treatment of dry borewells. So when we have observed that the borewells, whenever they dry, after giving the treatment with the shock waves, once again we can get the water back. What happens? The water is available in the borewell when water from the feeder source accumulates in the borewell through the number of seepage points. What happens? Inside the earth, there are some small seepage valley, like some seepage points will be there. So these are porous. So these are some porous points are there, and whenever these are blocked by some sand or other particle, so the water which is flowing, it is blocked. Suppose if we use the shock waves of very high strength, these whatever the blockages are there, so those blockages are clear, and here that they clear the blockage and regenerates the borewell into the water, and once again there is a free flow for the water. This is how it is used for the treatment of dry borewell. So this is something about the theoretical part associated with the shock waves. Many more such applications, biological applications or the industrial applications are there. Few we have listed here. The next one is one numerical we will solve, and with this we will wind up this particular module. See what is, let me read the numerical. The distance between the two pressure sensors, so those two pressure sensors, S1 and S2, in a shock tube is 150 mm. They are of 150 mm apart. The time taken by the shock wave to travel this distance, it travels 150 mm in 0.3 millisecond. If the velocity of the sound under the same condition is 340 meter per second, velocity is given, find the Mach number of the shock waves. So distance is given 150 mm and time taken is 0.3 millisecond. Now what is the shock speed? Speed is given by distance by time. The shock speed is us is d by t. What is the distance? The distance is 150 mm. Time is 0.3 millisecond. This is 150 mm 10 to minus 3 meter divided by 0.3 millisecond means into second. If you convert, it becomes minus 3. So it comes 500 meter per second. The shock speed is 500 meter per second. Then it is easy to calculate. What is the Mach number? Object speed divided by the speed of the speed of the sound in that media. So object speed we have calculated as 500 and speed it is given there in the given data. The speed of the sound in that it is 340. So 500 by 340 is 1.47. Therefore the Mach number is 1.47. Thank you.